Hello everybody, welcome to another math teaching video with Mr. Scarana. In today's video we're going to be talking about this idea called linear approximations, which is an application of our derivative work. So let's begin. Linear approximations. Okay, and what a linear approximation is, it's basically using an existing point and tangent line to approximate a nearby point, a nearby different point. So let's get into what this really means. So if we start with a graph, and I'm gonna draw this fairly large so you can see what's going on here. Just a basic, exponential looking graph. It doesn't matter what the graph looks like. But this basic graph, let's say we're at the point 5, comma, let's make that a 3. At the point 5, comma 3. Okay, so we're at this point right here. Now, if this function is f of x, whatever that f of x is, what we can do is we can use the tangent line at this point. Do we see how this tangent line very closely follows the curve? It very closely follows the curve. And so what we can do is we can say, well, if I want a point like 5.1, which I'm going to put right next to this, if I want a point like 5.1, and I don't know exactly what the value of f of 5.1 is, like if I say, well, what's f of 5.1? I don't know exactly what it is. What I can do is I can take the tangent line at this point, which closely follows the curvature of f of x, and say, oh, well, this point, I can use the existing point at 5, comma 3, and the tangent line that's at 5 to approximate the value here. And it'll give me some error. It'll give me some error, but what I can do is I can walk along this red tangent line a distance of 0.1, delta x equals 0.1. If I start at this point and walk along the slope of this tangent line a tiny amount, then I can approximate this value. So let's say the slope of this line equals 2, let's just say it's 2. Then what I can say is, well, I don't know exactly what the f of 5.1 is, but I know that f of 5.1 is going to be approximately f of 5, moving up the tangent line a tiny bit. It's going to be f of 5 moved up the slope of the tangent line a tiny little bit, 0.1. Okay? So if we're to generalize this a little bit more, we have f of 5.1 is about equal to f of 5 plus 2 is the slope at 5, right? It's slope, we can call this f prime of 5, right? The slope at 5. Which we just decided to be 2. So this could be f of 5 plus f prime of 5 times delta x. Okay? So really, if we're to generalize this any further, it would be f of our new point is approximately f of our known point. So you start at your known point. You move up the derivative of that known point, so the slope of that known point, a tiny amount. So what do we do? So f of some nearby point. So we can, using an existing point and a tangent line, we can say, oh, my new point is my known point moved up that tangent line a tiny amount. And this will give me an approximation, kind of gives me what happens at that red line, which you can see is very close to the true f of 5.1. And there's going to be some error. The difference between this approximation and the actual f of 5.1 is our error. And usually these errors are incredibly small. Usually you have to get to like 0.0001 off, right? Like they're tiny, tiny differences. So let's look at an example of what's going on here. I'm just going to move this down a little bit. All right, so let's look at an example here. So, example 1. Say we are given f of x equals x cubed. Given f of x equals x cubed, use the tangent line at x equals 2 to approximate the value. So basically approximate f of 2.01, okay? So we're going to use f of 2, the tangent line stuff with f of 2, to approximate what's happening at 2.01. So we can graph this. So f of 2 is 1, 2, 3, 4, 5, 6, 7, 8. F of 2 is 8, so it's going to be up here. All right, your general curvature of this function looks vaguely like this, okay? And so what we're doing is it's telling us use the tangent line at 2. It's going to be here. This tangent line. I'm intentionally drawing it, so it looks very close to the actual curvature. The tangent line, use that tangent line to approximate f of 2.01, which I'm going to exaggerate. 2.01 would be like almost on top of this line. I'm going to move it to here. Okay, so our delta x here is going to be 0.01. Okay, so we're going from 2 to 2.01. All right, and what we're trying to do is saying, okay, I'm just going to move along the tangent line a tiny amount, and that's going to approximate moving along the function itself, and it's going to give me some error. Okay, but it's going to approximate it very closely. If I move along the tangent line, that's a nearby point, right? 0.01 away. It's going to give me a very good approximation for the actual value. All right, so here's what we do. Let's take this concept, okay? So we have our f of our new point. Our new point is which is this, right? Our green dot. We're going to approximate it by saying, all right, well, it's approximately the value of our known point, right, which is this thing, and then moving up the tangent line, so the derivative of that known point, moving up its tangent line a tiny amount. All right? So f of new is approximated to f of known plus the derivative of the known point moved up a tiny amount. So what's our new point? So f of 2.01 is approximately f of 2 plus f prime of 2 times our delta x is 0.01. Okay? And so here, it's approximately, f of 2 is 2 cubed is 8. We're going to need to know what this is, so I'm going to drag this over to here and say f prime of x equals 3x squared. So f prime of 2 is 3 times 2 squared. 2 squared is 4 times 3 is 12. So 12 times 0.01. All right, so it ends up being approximately 8.12 if you move this decimal over. So 8.12. So we're approximating it and saying, all right, well, this value, if I move along the red line a little bit, that tangent line, this is going to be 8.12, which should approximate our actual value. It should approximate our actual value pretty closely. Well, I'll make that black. But this should be really close, right? So at 2.01, we say, okay, it's going to be about 8.12. Let's figure out what it actually is by using a calculator, right? Our actual value, so this is approximation, actual f of 2.01 is our actual value. 2.01 is, if you do this, it's 2.01 cubed, which in your calculator is about 8.1206. Okay, so that's your true value. I'm saying approximate because it's 4 decimals. I'll say it's equal to just for now. Our true value is 0.1206. So our error is really small. Our error is 0.0006. It's this minus this, right? Our error is 0.0006. So we got really close. So our approximation, moving along the tangent line, got us basically the value itself with a tiny amount of error. Okay. All right. And now, what is this useful for? This is useful for a few things. One of the things it's useful for is we're going to use this. I don't have space. Yeah. No. I'm going to erase it. All right. All right, so how is this useful? What can we actually do with this? Well, here's one of the things. One of the things we can do is we can estimate the root, whether that's square root, cube root, etc., of any number. Okay, so that's one of the things that we can do with this. Here's an example. I'll call this example 2. Here's our example. Let's estimate the square root of 50. All right, well, square root of 50, we don't know what the square root of 50 is. But let's see if we can walk through this. Well, for estimating the square root of 50, let's start by saying, all right, let's just treat this as the function f of x equals the square root of x. Okay, so it looks like this. All right, and I'm going to move out 10, 20, 30, 40, 50. Okay, now we don't know the square root of 50. We know the square root of 49 though. Square root of 49, we know that that's going to be 7. Try to get this right. So that's what our function looks like, and we know that the square root of 49, so there, 7. So now the question becomes, what's the square root of 50? What we can do is we can use this linear approximation idea. We can say, all right, well, let's take the tangent line at 49. You want to approximate 50? Root 50? Okay, let's take all the information we know about the square root of 49 and then say, all right, well, the square root of 50 is going to be approximately, it's really going to be here, right, along the black line, but if we don't plug that in, we can say, all right, well, let's just use this red line, the slope that happens at 49, to approximate it, and again, we're going to have some tiny little error, but it's going to be very small. All right, so here's what we do. You say, all right, f of our new point, which would be f of 50, is approximately our known point, okay, plus moving along that tangent line, f prime of known, you're moving along the red line of your known value, right, 49, times your delta x. Okay, so f of 50 is approximately f of 49 plus f prime of 49 times 1, right? Delta x is 1. The difference between 49 and 50 is 1. Okay. All right. So this is going to be approximately f of 49. We're using square root of x, right? So square root of 49 is 7. The derivative of this, let's do some derivative work. I'll rewrite this, x to the 1/2. You know you're going to have to take the derivative, so might as well write it in the polynomial form. 1/2 x to negative 1/2, which is the same thing as 1 over 2 root x, if you simplify it. Okay. And so f prime of 49 is 1 over 2 root 49. We're just plugging this in. Derivative at 49, I found the derivative to be this, so I'm plugging 49 times 1. This becomes approximately 7 plus root 49 is 7, so 2, 14. 14, which is approximately, if you do some little calculator magic, 7.0714. That's our approximate value. That's what we would get along the red line. Here, it's going to get really weird because you're going to get cramped, but 7.0714. This is the approximate value. The true value here is, well, just put in your calculator, square root of 50. Square root of 50, true square root of 50 actually equals, if you plug it in your calculator, 7.0711. So we're really close. 7.0711 versus 7.0714, our error is really small, 0.0003. Okay? So what I'm trying to get us to see here is that if you have some unknown value and you want to figure out what its value is, you can take something known that's adjacent to it and say, all right, let's move along the tangent line of that known value a little bit, because that approximates the actual curvature of the function. And say if you move along that tangent line a little bit, you're going to get really close to what the actual value is. That's it. Okay. Last example we'll do. So we did estimating the root of any number, and then now we can estimate the value for trig for any number. So we will do this. Okay. So here we're going to estimate trig for any angle. All right, cool. So let's do an example. This would be example 3. All right, let's estimate sine 31 degrees. Okay. First thing we want to do with this in general trig is we want to translate it to radians. So I'm going to make this sign of, well, 30 is pi over 6, and 1 degree is pi over 180. Okay, and we'll probably talk more about these in class. But really it's sine of pi over 6, that's plus sine of pi over 6 plus pi over 180. All right, if we're to graph this, all right, I'm just going to go from 0 out to pi over 2, 1, so it looks like this. And it keeps going, it oscillates, but I just want to try to cramp us in a little bit here so we can see more of what's going on. Pi over 6 is here, and that value, pi over 6 is here, and that value is 1/2. So sine of pi over 6 is 1/2. And so what we're trying to say is, let's use this. So here's what we know. What's known that's next to pi over 6 plus pi over 180? Well, pi over 6 is close to pi over 6 plus pi over 180. So we would use the tangent line here as an approximation, given our delta x is this pi over 180, right? Tiny delta x. All right, so that goes to there. And now we're saying, all right, we'll just move along the tangent line at pi over 6 a little bit, and that'll approximate the actual function itself. And so it's, a lot of this ends up being the exact same logic, right? We want to use the function, we already wrote it out, but we know our function here, if we're doing sine of 31, our function needs to be sine. Right, so it's function sine of x, just like when we did square root of 50, the function of square root. Now we're doing sine of 31 functions. Sine of 31 function sine. All right, and we know we're going to end up taking the derivative of this, so we can just do it now. F prime of x equals cosine of x. All right, and so now we have the value at our new point, f of our new point, which is going to be 31 degrees, okay, is approximately the known value plus moving along the tangent line of that known value, some delta x. Okay, so I'm taking our known point and moving along its tangent line a tiny amount, and that approximates the actual true value. All right, so f of pi over 6 plus 180, or pi over 180, we can write it like that, is approximately f of pi over 6, that's what we know, plus f prime of pi over 6 times our delta x is pi over 180. Okay, and so from here, we can say f of, this is 31 degrees, right? So I'll just write it there. F of 31 degrees is approximately f of pi over 6 is 1, well, I'll write it out. Sine of pi over 6 plus cosine, because f prime is cosine. So cosine of pi over 6 times pi over 180. Okay. I'll leave this as, I'll put this as pi over 6 plus pi over 180, that's fine. All right, that's 31 degrees because it's 30 plus 1 degree. So I'll say, all right, f of, now I'll write it, 31 degrees is approximately sine of pi over 6 is 1/2, which is our starting point, right? It's always going to be our starting point. Our starting point is 1/2, and then moving up the derivative a little bit. And the derivative of cosine of pi over 6 is root 3 over 2. That's the slope, times pi over 180. All right, now if you throw this into the calculator, it becomes approximately 0.5150, which is kind of what you'd expect, because this 1/2 is 0.5, right? So you're going to move up a little bit, so 0.5150. To be clear, the slope, so what you're doing is you're taking your starting point, which is sine of pi over 6, your known point, and then moving up its derivative a little bit. And what is the value of this derivative? What's the value of this slope? Well, it's root 3 over 2. So here the slope is root 3 over 2. All right, the derivative of sine is just cosine. So the derivative of sine of pi over 6 is cosine of pi over 6. So it's root 3 over 2. So that's your slope, root 3 over 2. Slightly less than 2. Okay, and then so now that's your approximation, and if you were to plug it in, right, your true value, if you will, is, so we know that regular old, I'll write it here, sine of 31 is 6 in a calculator, sine of 31 degrees, make sure your calculator's in degrees, is 0.51, sorry, This is point. Yeah. 0.5152. Okay, so now your error is 0.0002. All right. And that gives us what we want. Okay, this gives us the error. And it gives us, well, we don't really want the error. The error is just to see how far off we were. What we really want is this. We want the approximation, so 0.5152. And so hopefully this result is interesting to us. What we're able to do is see how moving along a tangent line gives us a really good approximation of actually moving along the function itself. All right, thank you very much. I'll see you in class.